All right, so why don't we get started? Welcome back to the 140 of you who are here. It's, again, great to see such a large and diverse PLMW. Lindsay covered this in her welcome talk, but PLMW has both some sort of explicitly mentoring talks like Derek's. These are sort of nuts and bolts talks about how to be effective as a researcher and even what is research, as well as some more technical talks that try to introduce you to some of the big ideas that the functional programming community is exploring right now. So this session is going to have 3 talks, and 2 of them are sort of technical talks that will try to give you an introduction to an area, and then we'll have one talk in the middle that's more of a mentoring talk. So for the first talk, it will be given by Nadia Polikarpova from UCSD. Nadia is a researcher working between several areas. So her PhD was sort of in software engineering at ETH, and she draws on ideas from sort of programming methodology and software engineering in a lot of her work. She also has a background in formal methods, in particular automated theorem proving, and she's been applying these ideas in the context of programming languages. So looking at how we can design languages that use things like constraint solvers and SMT solvers to automate processes that have been manual before. So this is one of the kind of hot areas in programming languages generally right now. And I just love Nadia's work because it draws on the kind of awesome, mysterious black box power of these solvers, but also brings deep ideas from semantics and type systems to help guide these solvers to be more effective. And she's going to give us a crash course on these constraint-aided tools. So take it away, Nadia.
Thanks, Nate. Thanks for a great introduction, your kind words. Let me start sharing my screen. All right. Okay, so like Nate mentioned, I'm Nadia. I'm an assistant professor at UC San Diego, and I work these days mostly on program synthesis, also on program verification a little bit. And today I'm going to tell you about how to use constraint solvers, and in particular SAT and SMT solvers, when you're building PL tools. Why did I decide to talk about that? Well, if you have been reading PL papers lately, you probably noticed that often they say something like, we used the Z3 SMT solver in the backend, or we solved this problem by reducing it to these SAT constraints or to these SMT constraints, right? So basically, SAT and SMT solvers are this invisible workhorse of PL tools, and they have been applied traditionally in hardware verification, software verification tools, program synthesis, and lately in these more new and exciting areas like network configuration synthesis, something that Nate is actually involved with, biological modeling, even architecture, right? So what I'm trying to say is this is this incredibly versatile, powerful, mature technology that is just there, you know, at your disposal. And you should at least, as a PL researcher, I think you should at least know about it. And if you're not using the solvers in your tools, you might just be, you know, missing out, right? So it's good to know about this. Okay, so for those of you who have never used those tools, never maybe even heard about those tools before, so what do these acronyms SAT and SMT even mean, right? So SAT stands for Boolean satisfiability. What this means is that a solver takes as input a propositional formula, and it finds a satisfying assignment for that formula. So in less fancy words, a propositional formula is just a Boolean expression where all variables are Boolean. And the satisfying assignment is just values for those variables that make the formula true. So an example of a propositional formula is right here, gin or tonic, where gin and tonic are Boolean variables. So let's say what I'm trying to do is to model this problem where I walk into a bar and I need to get a drink, and the only ingredients they have is gin and tonic, right? So I need a drink, so I need to get either gin or tonic or both. But let's say we want to add more constraints to this problem, so we'll add more clauses to our formula. So we also know that if I'm a minor, I cannot get the gin. And let's pretend that I'm 20 years old, right? So I'm a minor, right? I can give this formula to a SAT solver, and it will find a satisfying assignment for me. So values for these variables that make the formula true. So in this case, there's a single satisfying assignment which basically tells me that I can get the tonic, but not the gin. That's too bad. So in general, this problem of finding the satisfying assignment is NP complete, but modern solvers exploit the regularities in the realistic, SAT constraints to be able to solve formulas with up to millions of variables and millions of clauses. So this is all cool. Where does this other thing, the SMT, come in? Well, we need an SMT solver because not everything in the world is a Boolean. Not everything is modeled very conveniently as a Boolean. So let's say I have the same problem where I want to choose a drink, but I want to model some parts of this problem kind of more faithfully, right? So I want to say that, the restriction on minors not being able to get alcohol, I want to model as if my age is less than 21, then alcohol by volume has to be 0, right? And let's say I know that my age is 20. So here I'm using both Boolean variables, the blue ones, and integer variables, the red ones, right? And I want to use some, inequalities and maybe some arithmetic. And also, and this is true, I just checked Wikipedia and it says that in the United States, gin is defined as an alcoholic beverage of no less than 40% ABV. So I can add another constraint and say, well, gin implies ABV has to be greater or equal to 40. So I can give now this constraint to an SMT solver, right? And it will find a satisfying assignment for me for both the Boolean variables and the integer variables, right? So in this formula in particular, we use something called the theory of linear integer arithmetic, which is basically just fancy words for we were able to use integer variables, arithmetic, and inequalities, right? Equalities and inequalities over those. This is a very popular theory that a lot of SMT solvers support. But some other interesting theories that you might find useful are theory of arrays that you can use to encode things like sets and multisets, uninterpreted functions, bit vectors, strings. So which theories you want to use depends on what kind of domain you're trying to model, right? What kind of problem you're trying to model. Okay, so today I'm not going to tell you about how these SAT and SMT solvers actually work under the hood, because this is a research area in itself. But thankfully, as PL researchers, we don't actually really need to know that because there are a bunch of industrial strength tools that are available that we can use just, off the shelf. So some popular SMT solvers include Z3, CVC4, Yikes, Bool Lecter. So what's really nice about all these solvers is that there's a standardized input format that they all accept. It's called SMT lib. And so if your tool generates constraints in SMT lib, then you can use all of the solvers interchangeably. But of course, sometimes it's nicer or more convenient or more efficient to use specific language bindings or an API for each solver. And we'll see example of that later in the talk. But then of course, the downside is that you're using something that's specific to the solver. You can't use them interchangeably. Another nice thing is that there's an SMT competition that happens regularly. So you can simply check out the results of the latest competition to see, what's the newest and hottest solver for each area right now. So in particular, among those, I would say Z3 is the most popular solver that's used in PL tools, basically for two reasons. First of all, because it's reasonably good at many of these different theories that I was mentioning. So it would be good at modeling many different things, but also because it has really nice APIs, right? These language bindings that I was talking about. Okay, so my plan for the rest of today is to show you how you would use Z3 to solve some tasks that are common when you're building PL tools, right? In particular, 3 tasks. First, how would you use a solver to implement constraint programming or declarative programming? Second, how to use a solver to implement program verification. And third, program synthesis, right? So basically, I'm proposing that you and I together build a program verifier and a program synthesizer right here, right now from scratch in half an hour, which sounds crazy, but I'm not completely crazy. So we will restrict ourselves to make our life easier. We'll restrict ourselves to solving just one particular problem, right? our verifier will only work on basically one program, right? But hopefully you will see how to extrapolate from that and do this in a more general case. All right, so what is this problem? One problem that we're going to focus on. The problem is called array partitioning. So you have an array of size n, and you want to partition it evenly into p subranges. So this is quite easy to do if n is divisible by p, right? Then you simply assign n over p size to each partition. But it's a little bit harder to do if n is not divisible by p. So a naive solution that you can think about is, well, let's just assign n over p to the first n-1 partitions, and then assign the rest of the elements to this last partition. Well, the problem with that is this division is not particularly even, right? So our last partition now has many more elements than all the other ones. And this might be a problem if what you're trying to do is do some kind of like work partitioning, right? So if you have p threads and you're trying to process the elements of this array in parallel, then in this case, your last thread will be stuck doing a lot more work than everyone else, right? So ideally, what you would like to do is, partition it more evenly this way, and more generally, you would like your partitions to always differ by at most one, right? And now our question is, can we make this work for every n and p, right? So of course, if you're a good programmer, you would think for a little bit about this problem, and we'll figure out how to assign each one of the sizes based on the values of n and p. But our goal today is not to have to think very hard and delegate all the thinking to the solver, right? So our goal is to use Z3 to solve this problem for us instead of us having to think about it. Are there any questions until this point? I guess not, since Nate is not interrupting me. All right, so let's jump in and just, see how we can do that. So today, I'm going to be using the Z3 bindings for, the Python bindings for Z3, because I think out of all of the language bindings, these are probably the nicest and the most seamless to use. So to be able to use Z3 from Python, I simply say, from Z3 import star, and now I have a solver at my disposal that can solve constraints. All right, so we have, let's say we're interested in n equals 10 and p equals 4, and what we're trying to do is to assign a size for every partition from 0 to p minus 1, right? So instead of having to put a particular expression into here for size, right, I want to ask the solver to do this for me. So first, the first thing that I want to do is I want to create the solver, right, so that I can later use it. So I can do it this way. And so now we are going to assign to each size, the size of its partition, a symbolic value instead of assigning it a concrete value, right? Meaning that we will ask the solver later to figure it out for us, to solve for this value for us, right? So we're going to do it this way. So it's going to be an integer variable with the name size, plus, since we want different names for different variables, we're just going to index it with I, right? And so now it's time to add some constraints to our solver. So to add constraints, we just use this s.add method, but what are the constraints that we want to add? So the thing that we really cared about, remember, was that the partitions are even, right? So even partitions. So the way we're going to say that is we're going to go through all of the pairs of partitions and then assert that they differ by at most one, right? So we're going to say for I in range P, and for J in range P, the constraint that we're going to add is that size of I minus size of J less than or equal to 1. Okay, so the first thing that we're going to do is we're going to ask the solver to display all the constraints that we just added just for debugging purposes, right? Because, it's sometimes hard to imagine, what this all looks like before we see it. So now if I run this file in Python, so I will see all the constraints that I just added, and those look right. Yeah, so I wanted, between all the pairs of the size variables, I wanted the difference to be at most 1. Okay, cool. So now the next thing that we can do is we can ask the solver to actually solve these constraints, right? So to do that, we do s.check. And if we print the result of that, oops, we'll see that the solver says sat, right? Sat means it found a satisfying assignment. But of course, what we want to know is not just that it exists, but what this assignment actually is, right? So what we want to actually do, if s.check equals sat, we want to print something called s.model, right? Model is the solution to the constraint, the satisfying assignment. So if we do that now, we see, okay, great, it found the solution, but the solution is not particularly interesting. It just decided to assign zeros to all of the sizes, which of course satisfies all the constraints that we actually asserted. But why is this happening? Why is it not generating a more interesting solution? I'll just give you 5 seconds to think about it. Well, it's because we forgot to add another important constraint. Our other important constraint was that the sizes should add up to n, right? So add up to n. How do we assert that? So we do s.add again, and there is a convenient function sum in the Z3 API. So we can say the sum of all the sizes should be n. Okay, so and if we run this now, now we're getting some decent sizes, right? So we're getting 3, 2, 2, 3, which is basically what we saw on the slides. Okay, and then we can, we can try it with other values. And of course, if we do it, if we make n 9, we'll get 2, 2, 2, 3. If we make n 11, we'll get something like 3, 3, 2, 3. Okay, so it seems to be working correctly. So let's go back to 10. So essentially, what we have seen right now, so what I was trying to emulate is using Z3 to implement a language that has constraint programming or declarative programming capabilities. Of course, in a real language, so what you will have to do is to somehow programmatically translate the constraints that your users write in the language into the Z3 constraints. We did it now by hand because we are only dealing with one program. All right, so constraint programming is great, and as you can see, quite easy to implement using these solvers. But the problem with constraint programming is that it's not particularly efficient, right? Because the idea is that we will have to solve constraints at runtime for every specific value of our inputs n and p. And this is not, of course, always what we want. Sometimes we want something more efficient. So another scenario for using solvers is we write a program in a traditional way, let's say in a functional or an imperative way. And we use the solver to verify that this program satisfies our specification for all inputs, right? All inputs. That's called program verification. So let's see how to modify our encoding to do program verification instead. So let's see now, after we have seen what the solver did for, n is 4 and n is 10 and p is 4, we have some kind of an idea for what the general solution might look like, right? So we know that we want to assign n over p to some of the partitions and n over p plus 1 to some other partitions, right? And essentially, we just need to decide how many of the partitions, let's say we want k of the partitions to be of this larger variety, and we just need to decide how many of the partitions should be larger, right? So now to encode that solution, instead of the sizes being symbolic variables, what I'm going to do is to actually assign it an expression. So I'm going to assign it a symbolic conditional. right? And I'll say if I is less than some k, then I'm going to make it n over p plus 1. Sorry, large p plus 1. And otherwise, I'm going to make it n over p. And so the only question is now what k should be, right? So from our one example of 10 and 4, we know the k was 2 in this case, right? But this might be because either it's always 2 for all inputs, or perhaps k is n over p, right? Because 10 over 4 also happens to be 2, right? And or perhaps k is n mod p, because 10 mod 4 is also 2. So we're trying to figure out what is the generalizable expression for k that actually works for all inputs. Okay, so now again, our motto for today is we don't want to think very hard. So instead of trying to decide this ourselves, we're just going to try all these different possibilities that we came up with and ask Z3 to check for us whether any of them works for all inputs. Right, so this is what we're going to do. So how can we check whether it works for all inputs? Well, naively, we could maybe write a big loop and try all possible n's for all possible in 32s or something. But that would take a really long time, and it would take literally infinite time if we're interested in all mathematical integers, right? If we don't actually have any bound on what n could be. So instead, what we can do is we can make n symbolic, right? So we can say n is a symbolic value now, and we can ask the solver to find an n for us such that the constraints are violated, such that our implementation does not satisfy the specification. So just an aside, in a real verifier, of course, we'll make all the inputs symbolic. We'll make p symbolic as well. But since we don't have much time today, we're going to focus on, p is 4, once and for all, but we're going to verify it for all n. All right. So what should we do now? We made our n symbolic, and now we want to ask the solver for which n is can each one of these constraints be violated, right? So essentially, we want to negate each one of our constraints. So we want to say, what is the n where the negation of these holds? Right, and what we really want to do is, if this happens to be satisfiable, it means that we found an error. We found a counterexample, right? So here we want to report an error, we want to complain. We want to say something like uneven partition, and print the model. And we want to quit, right? Because now we found the error and that's it. And if the constraint was unsatisfiable, it means that this particular constraint holds, but we want to continue and check the next constraint. But we have to be careful because we just keep adding the constraints to the solver. And if the first constraint we added happens to be unsatisfiable, then the next time we add a constraint, it's only going to be more unsatisfiable, right? So in fact, what we want is to remove the constraint again before we check the next one, right? So we can achieve that by saving the state of the solver before we add the constraint using s.push. And then at the end, after we check that, we can restore the state by using s.pop. Okay, and we want to do the same thing here. We want to negate this. Say, find me an n where it does not add up to n. And so if this constraint was satisfiable, then we want to print an error. So like print does not add up to n and exit. Oh, sorry, print the model first. And exit. And here, in principle, we should also do the push and pop thing, but this is the last constraint that we're adding, so it doesn't really matter. And then if we got to this point, right, so if we never violated any constraints, it means that now we have verified all our constraints, so we can print, something like a success, verified for all n. Okay, cool. So let's see what happens if we run this. So we found an error, right? So what the solver is telling us, so it's printing, it's telling us it does not add up to n for n equals 0, right? And so let's say we also want to know what the sizes of partitions actually were, because right now it's a bit hard to debug. So what we can do is we can ask the model to evaluate some values for us. So we can say for x in sizes, we want to evaluate these different sizes under this particular model, right? So we can say as.model evaluate x. Okay, let's run this again. And we see, well, of course, so for n equals 0, the sizes that we are assigned were 1, 1, 0, 0, which is understandable because we basically said, you know, assign 1 to the first 2 sizes, right? And 0 to the other ones. Of course, this does not add up to 0. Okay, so let's try our other options for k, right? So if I try n over p, what happens? Oh, so it found another counterexample. Apparently, it does not add up to n for n equals 12, right? So if n equals 12, then n over p is 3. So we have 3 of the larger partitions, 4, 4, 4, and one smaller one. This does not add up to 12. Okay, so how about we try n mod p? Hooray! So this one worked, verified for all n. So this is actually the solution that we're looking for. And remember, for all n here means for all mathematical integers, right? So this was pretty impressive. Are there any questions at this point? Because this is the end of the verification part.
There have not been many questions, but I wanted to point out if folks are on the Zoom, Cloudera had a brief outage about 15 minutes ago. So if you were locked out, try again. You should get in now.
All right, cool. So just to sum up.
Actually, there's a question here.
Okay, cool.
Just came in. So where do you enforce that n is greater than or equal to 1?
Oh, we don't. So I mean, n can be 0 as well, so that's fine. So for negative n's probably don't really make sense for this problem. It's somehow like the math still works out, even for negative n's apparently. But if you want to enforce something like this, then you can, right? So you can say that you can enforce a precondition that says, you know, n greater or equal to 0 here, right? And you know, this will still all work out the same way, right? So similarly, if we have a solution that doesn't work, then you know, it will still find a counterexample. Good question. Yeah, so you can enforce preconditions on your inputs in this way, just by simply by asserting those constraints into the solver. Cool. All right, so we saw how to use it, the solver, for program verification. But what was a little bit annoying or maybe unrealistic in this example is that you know, we had to come up with all of these potential candidate programs, right? And in this case, we happen to have, you know, 3 candidates, so it wasn't too annoying to check all of them. But in reality, you know, the programmer might not have a very good idea for what the candidate programs are. Or there can be too many of them. So this is where program synthesis comes in, right? So the idea of program synthesis is, how do we make the solver search for the right program for us, right? And kind of automate this kind of program selection process. Okay, so basically what we want to do is, here we still think that, you know, we have these 3 program candidates, except we don't want to try all of them one by hand. We want to ask the solver to pick one for us. So how are we going to do that? Let's, for this one, switch back to the version of our constraints that is positive, right? The one that are non-negated constraints, the ones that we had before we started doing verification. So I have this version right here. And so let's say now we're interested in a particular input, which is n equals 10. You know, for little unimportant reasons, I'm leaving this n as a symbolic value here, but I'm fixing it to be 10 by simply asserting that n is equal to 10. Okay, so now I would like to the solver to help me pick between these 3 programs. So to do that, I will introduce another variable that I will call a control variable. And the idea behind this control variable is I want to index my space of all programs by this variable, and then ask the solver to pick a value for this variable, which will mean the same as picking a program out of the space, right? So I'll call my control variable C, and I'll make it integer. And the idea is we want, so because we only have 3 programs to pick from, we want this C to be, something between 0 and 2, right? So I'll say C is, between 0 and 2. And I will index my space by C, which means that I will make K like a big symbolic conditional, right? Like a big switch on C. So I'll say if C is 0, then K should be 2. And otherwise, if C is 1, then K should be, N over P, and otherwise it should be N mod P, right? So you can see how, depending on the value of C, K will be a different expression, right? And again, this is a very simple example where there are only 3 programs in the space, and that's why it's pretty easy to see how to index them by C. But you can imagine, like in reality, there will be a huge space with like potentially thousands or millions of programs, but you can still use the same idea to index them all by 1 or more of these control variables, and basically make it into this big conditional, right?
So Nadia, a couple of questions and a quick
Uh-huh.
time check. So I think we have about 7 minutes left at the time check.
That's
and
cool.
Then the question,
Yeah, we're almost done.
So the question is, why do we negate the constraints one by one, pushing and popping, instead of just checking if the negation of the previous complete constraint fails?
That's a really good question. So we could simply, collect all the constraints together in one big conjunction, right? Then negate this whole thing, and that will be fine, except that this is bad for debugging, because then the solver basically say, well, yeah, like the whole thing just failed, but we don't know, for example, whether it was the uneven partition condition that failed or the does not add up to n condition that failed. This way, you can actually get better information on which constraint exactly failed.
And a second quick question, the int constructor takes a string which was n for both the n Python variable and the
Oops, yeah, that's a typo.
Okay, great.
Thank you so much. Yeah, this is the name of the variable. So that would have failed miserably if I tried to run that. Thanks. All right, so let's run this, the synthesis one. And so basically, we're expecting it to tell us, what should C be for the constraints to hold. And now it's telling us, well, C should be 0. It means that it's picking the expression 2, right? And that's not very surprising, because we know that for n is 10, actually all 3 of these expressions work, right? So it doesn't really matter. It just picked like the simplest one, right? So it picked the expression 2. So now we can go back to our verifier, right? And check whether this expression 2 actually works for all inputs, right? So let's do this again. And it says, no, it doesn't work for n is 0. We have seen this before. So we can go back to our synthesizer and say, well, synthesizer, how about you find me something that works for n is 0, right? So you find me some C that works for n is 0. And I run the synthesizer again, and it says, oh, C equals 2 works for n is 0. C equals 2 is n mod P, right? So I go back to the verifier, and I say, okay, so the synthesizer said it should be n mod P. Let's verify that. And then the verifier says, hooray, it's verified for all n. So now we're done with the synthesis, right? So we use this collaboration of synthesizer and verifier to find a program that works for all n. And so this process that I showed you is called counterexample guided inductive synthesis, or CGIS. So in general, you would start with some arbitrary input, like we had 10, right, for n0. We ask the synthesizer to pick a program or to pick a value of control variable that works for that input. So let's say it picked some C. Then we use that C to verify whether this program works for all n. If it does, then we're done with the synthesis. If it does not, then the verifier will give us a counterexample, will give us a new n. In our case, it was 0. that we add to the set of interesting inputs, and then we ask the synthesizer, well, give us something that works both for 10 and 0. So we only asked it for 0, but in reality you would ask, give me something that works for both for 10 and 0. The synthesizer says, okay, so I think c = 2 works for both of them. Then we verify that, and it's done. So in general, they can be, of course, take multiple iterations, but this is how you can use SMT solver as both a synthesizer and the verifier in this loop to synthesize a program that satisfies all of your constraints on all inputs. Right, so this is basically what I had for you today. Just to sum up, I showed you how you might use an SMT solver to implement some declarative programming, program verification, program synthesis, and I hope it was useful. Thanks.
Thanks. So we have time for a few questions before we switch to the next talk. And one of the questions is asking about rewatching events. So we will post videos for speakers that are willing to allow them, and those will be disseminated, I assume, on the PLMW webpage. It won't be immediate though, but you will have a chance to rewatch, I suspect, most of the presentations in the future. So one question from Clouder, say I want to solve the Gödel number of a program that satisfies some constraint. Is that going to be practical?
So I think a good way to rephrase this question is, how do we build this correspondence between the control values and the programs, right? So I think that there will be a fair rephrasing of this question. So indeed, it's actually important how you do that, right? So essentially, you need to build it in such a way that okay, if you have a space with 1 million programs, and you simply kind of like enumerate the whole space, print out all the programs, and then put it in one big array, and then tell the synthesizer, okay, pick one of this out of this array, that's not going to be very efficient, because essentially there's no structure to it, right? So it's just like a linear representation of all of those programs. So the solver is not going to be able to find it very quickly, right? So, and this is essentially what we did here, right? So this is not very efficient, but we only had 3 programs. So what you want to do is sort of, because your program space will have some structure. So for example, you'll say, well, I mean, maybe my top level construct is a conditional, and then there's some subspace for the first branch and some subspace for the second branch, right? In this case, you want to map it in such a way that you have a control, a separate set of control variables representing what's in the first branch of the conditional and what's in the second branch of the conditional, so that the solver can sort of pick them independently, right? Based on independent constraints that pertain to each of the branches, right? In this way, it can sort of explore this structure in the program to be able to solve these constraints more efficiently. And a very good paper to read if you're interested in how to encode programs as constraints is Armando Solar-Lezama's, I believe, 2013 journal paper about Sketch. I think it's called Program Sketching, right? So the Program Sketching paper has a very nice introduction, I think, to how to encode programs into constraints.
Great, thanks. So I think we're actually out of time. So there's lots of questions coming in on Clouder, but one of the cool things about a virtual conference is that we can continue the conversation in the chat. So Nadia, if you want to jump on there, you can answer some of the questions that are coming up. And perhaps the next break, I think we have a lunch break at noon, or 12:30, sorry. I think it's 12:30 Eastern time. We can create some coffee chat rooms or other rooms to keep answering questions. So thank you so much. That was a great introduction to solvers and verification and synthesis. And see you at the rest of the conference.
Yeah, thanks for inviting me.